Now I can record. So homework 5 was due today, which means homework 6 is due next Tuesday. We're going to continue to work on lab 3, measuring propagation delays, and Max understands how to do it fairly well. I understand how to do it fairly well. You will have some trouble figuring out how to do this. I don't know how to write this down and explain it. I have to look at what you're doing and help you. It's a small enough class, we can do that. We have enough TAs, we can do that. So we'll finish lab 3 this week, and the quiz will be the following week. I'm not going to be there for the entire lab. I'll probably be there for like the first hour because I have to get down in Phoenix and get my second COVID shot. Lab quiz will be the following week. And our next exam is Thursday, March 25th. You need to make an appointment for a remote exam, or you can take it in class. And you know how to make an appointment for a remote exam now. I will try to get everybody to come at the same time, and if that doesn't work, I'll find a second time. Let's see who that was. That was Gabriel. And Victor, I've already got. Okay. Oh, let's just put this back. Let's see. That is now. Classes for fall 2020. Yes. Oh, yes, you do. Sorry. Power on. I got the cable hooked up at least. You see, the hair is lined with aluminum. Okay. Classes for fall 2021, 490 embedded mixed signal design. Hopefully we'll be back on the bench and everything will be okay. If you're interested in an undergrad internship in cryptography, take INF 638. We have money for undergrad students. It pays better than anything else at NAU. What? Yeah, well, you should. I pay you. I pay you, at least minimum wage in Flagstaff. The lab pays what the Dr. Cambo thinks is minimum wage in Flagstaff, and I've never told him he's wrong. As a grad student, you get paid more than that, but and it's actually kind of some interesting work. Yes, we're doing 188 with transistors. We talked about this. The idea is we want the circuit in saturation, so we have a slope. And if I put my input on this, my input voltage on that voltage transfer curve for a inverter or for any circuit is VGS. My output axis is VDS. I put a small change in VGS, and because of the slope, I get a big change in VGS. This is the workhorse, the common source amplifier. We'll talk about the other types of amplifiers. Then we'll talk about how to put them actually inside an integrated circuit where we can't use resistors anymore. Resistors are really expensive because they take up an amount of room that you can actually see, and transistors are tiny, so I'm going to use a transistor as a resistor, basically, is the idea. We'll get into some of that today. When you're doing the DC analysis of these circuits, always check Ohm's law, check for KCL, check for KVL. Write down everything you know on the circuit and everything you can find easily without worrying about what the problem's saying. And then if you know VGS and you know the size of the transistor, you can calculate ID. If you know ID and you know the size of the transistor, you can calculate VGS. So those are the easy things to go for first. And then once you get the IDVGS thing going, you can go and try to reapply Ohm's law and KCL and things like that, and you will get most of what you need on this DC analysis. Nothing really complicated like the 188 circuits I was yelling about in the meeting yesterday. This is an op-amp. Let's look at this. I've got my output voltages right here, and this is actually a dot. It's connected. So the output voltage is going through, coming from the input, because the input's over here, so it's coming through that transistor. I'm kind of backtracking through the signal path, and I have to get to, I can't explain this yet. But this transistor here has the inputs on the gate, the outputs on the drain. This is a common source transistor, just like we're talking about today. And we'll talk about some more of the pieces in there. Most of the transistors in this circuit fall into two categories. They're either signal gain or they are current sources. I can look at this and I can pretty much tell you all this down here is nothing but current source. And this is current reference too. The gain transistors are in here. There's a few pass transistors. There's a really weird diff amp. Other than that, you can kind of, when you start to see the pieces of this, you can kind of like figure out how it goes together. No one's going to ask you to redesign the 741 op amp your first week of work. Now, the general method, when the circuits change, they're going to change from common source to common gate, common drain, etc. There's not too many other things I can go beyond that. What's going to happen is we're going to have a general form that works where we don't have to do calculus every time. The general way to do this, first of all, we're starting out with these transistors, which are non-linear circuits, which means they have non-linear equations, which are even hard for a computer to solve. The way we solve them by hand and the way you solve them with a computer is I take the non-linear circuit and I approximate it with linear models. And we really only have a couple of linear things in our circuits: resistors, inductors, capacitors, voltage sources, current sources, and dependent voltage and current sources. So out of those building blocks, we want to give a model that pretty much approximates what the transistor does. For our hand calculations, there's only two devices in the model. For SPICE calculations, there's an infinite number of capacitors around that also. But for our hand calculations, what we do in class and on the homework, and it's a good thing to have, not just because, and don't say I don't need to do this, I have a computer. You need to have an intuitive feel for how these circuits work so you can build them. And you get that from doing these hand calculations. First thing we do, we calculate the DC operating point. For me, this usually is the divide and conquer strategy. I draw the DC circuit here. And I can, if the circuit's complicated, I draw the DC circuit to simplify it. I find big ID, big VGS, and big VDS, which is my V out in this case. But this would be VDS. If I can get those three things, I can get to the next point. To do the small signal analysis, we use our linear transistor model to calculate the values, the GM and the RO in that model. I need these values right here. So I use these values to calculate the GM and the RO. And this gives me a linear model around that Q point. As long as my signal doesn't deviate significantly from that DC Q point, I've got a fairly decent model. It's called the small signal model. We don't want our signal to deviate from the Q point very much. We add the small AC and the DC together, and we get the total signal. So we're going to get through the small signal model today and some stuff on the common source amplifier. And I'll show you my amazing diagram. It's like key slides in 280. It's just one picture that makes doing all these things easily. Look at this thing right here. GM is the slope of this line. It's going to be our transconductance. It represents our gain. So this is the slope, GM. This value right here is the DC value of our current. This is the current axis. So this is big ID. Little ID would be the value that it's deviating from around there. This is my VGS axis. So right here I have my signal VGS. So that's little v, little g, little s. And the amount of my DC operating point, my DC VGS above VT, VGS minus VT is V over voltage. And this is this line right here represents my DC, big V, big G, big S. And this must be my signal voltage, little v, no, it's not, I'm plotting it versus I. This is little ID. Okay. As long as I don't vary too much around this operating point, I assume it's linear around that operating point. The body effect does have an effect. When we calculate the current, we're assuming it's in saturation, but our VT here is a function of V at speed. SPICE and things like that will take that into account. For the very first order hand calculations, we usually ignore the effect of VSB and consider VT to be a constant. Now you can ignore the body effect. But Metagraphics Multisim takes it into account. What we have here, we want to model the change in the change in current flowing from the drain to source. So the change in ID with respect to the change in the VGS, it looks like the derivative. It is a derivative. It's the slope of the line. The way we approximate it is instead of taking the slope of the instead of taking the derivative, is we take the slope of the line at that point, and we consider that to be a constant. From a circuit model perspective, we want ID. We need some kind of ID source here. I'm going to declare it's going down, and it is a ID that depends upon VGS, and this is little v, little g, little s. This is going to be GM, if we take this to be a constant. This is going to be GM VGS. And our constant is something, it's either GM or 1 over GM. Okay. So that's the most basic model I have. And the only thing we're modeling is the slope of that line, and we're treating it like it's a constant at our operating point. Oh, that is on there. I did get it right. It is GM. See, there's the equation, not 1 over GM. Okay. First circuit element we have. The next thing, most basic thing we want to model is that channel length modulation. We added the 1 plus lambda VDS to the current equation in saturation. We also modeled it as a parameter called little RO. And little RO was 1 over lambda ID. And this is modeling the slope of this line in the saturation region. Notice it's not a physical resistor. It is modeling a linear effect inside the transistor. I increase VDS and ID goes up. So we're modeling it like a resistor, but it's not a real resistor. Sometimes I still get bitten by thinking of it as being an actual resistor every time the current source rears its ugly head. VGS. This is GM. It's a current, it has a value of GM times VGS. And I stick another resistor, I stick a resistor out here that models the slope of that line. It's to make this physical effect look like a circuit diagram, so as engineers we can model it. Okay. This applies to every circuit. It doesn't matter how I connect up the transistors. I can use this model in the small signal. This is an AC model. We don't use it at DC. How many times are okay? I have to say it to myself sometimes too, to remind myself that's true. So there is my ID VGS equation. This is the basic one without the channel length modulation. We figured we could, remember we could add a 1 plus lambda VDS on here, or we can model the same effect, just get rid of this part and include RO in our calculations. And RO is 1 over lambda big ID, which is this part right here. Somebody caught me on the homework using little ID on the solutions. Yeah, that was a mistake. When we want to calculate GM, we've already gone through the rigmarole to calculate it for this common source transistor. And this works for any transistor, actually. You can calculate GM by the same method. We're not going to derive that, though. We can take the Kn of the transistor and multiply it by V over voltage. If we know ID and V over voltage, we can use this equation. If we know Kn and ID, but we don't know V over voltage, we can use that equation. I've seen people on exams tell me, look and go, I can't calculate GM. I don't have V over voltage in Kn. And I just look at it and go, yes, you can. Because I don't say this, but you have Kn and ID. So you need all three versions of that. Not just you can't use just one of them. This is just an expanded version of the previous one. The big thing we can get out of this is if RO goes up, what happens to RO if we double ID? If we make ID bigger, RO gets cut in half. If we double the width or double ID, GM will double. Either one of those will double GM. If I double ID, the output resistance goes down. If I double ID, GM goes up. I'm going to go ahead and just give this to you. We'll go through some derivations though. But if you ever have to guess what the gain of a transistor is, your best bet is GM times big RO. And big RO is related to little RO. It's not quite the same thing, but they're related. If you can figure out the output resistance of the circuit, you know GM, you can pretty much ballpark the gain if it's a reasonable circuit. Sometimes you have to put a minus sign out front. We'll go through this, and it all goes down to one magic diagram. I've conceptualized this down, this whole part of the course down to this one diagram that nobody understands. until like, 2 weeks into it, they'll go, oh, that diagram's important. When the daylight hits, you'll see it. And we will look at that one today. This is the small signal equivalent circuit. So if I want to draw the AC version of this circuit here, I'm going to put this model of the transistor into it. The first thing we do is we look at the circuit as it stands. Our DC voltage sources get deactivated. They become shorts. So this VDD up here is really tied to an AC ground. It's a DC supply, the AC part 0, so it's an AC ground. This little v, little gs gets deactivated, so it's shorted out. No, sorry, it's the big V, big G. We're doing the AC model. This gets deactivated, so we short that out, and we've gotten rid of a lot of stuff there. That's the AC part of the circuit with the transistor in. The AC part of the circuit, when I put the small signal model in, I just start out with this. Let me just do, oh, I have a pretty picture of it over here. Let's start with the pretty picture. On the drain of the transistor, right here, what I have is I have a resistor to ground, resistor to AC ground. So I put that in, RD. On the source of the transistor, I have a direct connection to ground, so I just put that in. And on the gate of the transistor, I have this AC source. This is about as easy as it gets, VGS, little v, little g, little s. That's the circuit I have to analyze. And I usually do this with a common source transistor by dividing it into two circuits mentally, because this is one circuit, it's just one loop going to ground. And it's basically telling me little v, little gs equals little v, little gs. That one's not hard. Over here, I have, this is connected to ground, this is connected to ground through the source, this is connected to ground. So all these things are connected together and connected to ground. Basically what I have is a current source going into the parallel combination of two resistors. So if I wanted to find, usually what I'm looking for is what is this voltage right here? VD, V equals IR. VD equals the current, yeah, let's write that down. VD equals the current times the resistance. In this case, VD, the current going into it, if we put VD positive up, is not obeying passive sign convention, so it's negative. The current has a value of GM VGS, and the R that current source sees is the parallel combination of little ro in parallel with RD. And little ro in parallel with RD in this case is my big RO. And we'll look at that. So I'm just dividing it up into two parts. If I want to find the gain, and this is not a, that should be a little letter. It's little v, little d. The gain is defined as the voltage out over the voltage in, always. In this case, my voltage out is little v, little d, divided by little v, little gs. I can just divide that equation and get minus GM big RO in parallel with RD. That's all I had to do. That magic trick works for every common source amplifier. The thing that makes this circuit analysis so easy is the fact that both the source is referenced to ground, and that drain resistor is referenced to ground. If I put a resistor into the source, it becomes a nightmare, which is why we use bypass caps. We'll talk about that later, maybe. So there it is. We've already done this. It's minus GM. I told you you have to guess it's GMRO. Big RO. We found out in this case, we'll talk about this, it's little RO in parallel with RD. Right now, that's your definition of big RO. We'll look at this in some more detail. The waveform parts, remember when they're little v, little g, little s, this is the AC part. Big V, big G, big S is the DC part. And little v, big G, big S is the AC plus DC. That's the total signal. You'll get to plot those in a homework or two. Use MATLAB because you can actually see what's going on in MATLAB. Your diagrams will be neat enough. You can read them. Right. We did that. So here we go. We've got an example problem. We want to do the DC analysis first, and then we want to look at these AC things. I've mentioned big RO. I haven't talked about big RN. But for the thing, we're given VDD, we're given VGS, we're given ID, we're given VDS. I'm going to write these down. Get in a good habit. VGS is 0.55. VDD is 1.8. We want, and we're given ID. It's 150 microamps. So we have enough information about that resistor. We got its voltage drop. We have its current. We can calculate RD. Ohm's law, RD, voltage drop is 1.8 minus 1.2. V equals IR, so V over I is 150 micro. You get, isn't it amazing to have an entire life where you have earned a living and know nothing but V equals IR? And people think you're like, you're good at V equals IR. Okay, so we got that 4K ohm resistor. We've got a value for that. We've got all the values we need to calculate. Well, we haven't talked about what they were in. So let's draw the circuit model. I am going to the AC circuit. How do I get there? I deactivate the DC sources. This one goes to ground. I draw my little AC model. I need more room. GMVGS. Little RO. This is the drain. This connects back to the source. And this is the gate. Okay. What we look at our circuit, the source is tied to ground. The drain is going to RD to an AC ground. It looks just like the last one, RD. And the gate is going to an AC source. I may talk about Thevenin here. Forgive me. Right. Take my jacket off. I'm going to talk about Thevenin. It's getting warm up here under these lights. Okay. We want to figure out what the input resistance is, what the output resistance is, and what the voltage gain is. So let's change colors here. Let's go to something really contrast. If I want to find the input resistance, because I want to do this on the same graph, what I have, Thevenin tells us that what I do is I deactivate the sources. Okay, this one gets shorted out. Thevenin's kind of, you didn't learn about dependent sources, unfortunately. I ground the other two inputs, so they're already grounded, and I find the equivalent resistance. The voltage, if I inject a voltage into the gate, how much current am I going to get? Yes.
Oh, sorry, I just had a quick question. Isn't the voltage across that open part of the circuit past the AC source that little big GV is? That was supposed to represent, or is it just the same as the source?
It's the same as the source in this case because I don't have any resistors in there.
Okay.
If I put some resistors in there, I would have to call my source like little VN or something like that. Okay. If I put a voltage where VGS is, I'm not going to get any current. It's an open circuit. There's no path for current to flow. That's telling me Rn, this wasn't as hard as I thought it was going to be, equals infinity. Which is actually an amazing thing. Now the next thing I want to do is swap colors. And I want to figure out what the output resistance is. Okay, this is RO. Now the trick to this is I get to ground all my sources. So I'm deactivating this one again. So if I ground the VGS, this little VGS goes to 0 too. If little VGS goes to 0, GM times little VGS is going to be 0. I've effectively deactivated the dependent source. So the only thing I see in here is the parallel combination of those two resistors. I'm going off Thevenin on you. RO equals little ro in parallel with big RD. The voltage gain is GM big RO. It's minus because this is a common source. So the voltage gain is minus GM big RO. I'm trying to teach you this shortcut starting out. See if this works. So it's minus GM. This is the same thing we got on the last circuit. It's the same circuit. Okay. Three things we want, and I might have that slide yet. I'm not going to talk about it. Oh, I hate this. That's not the hybrid pi model, Dr. Brower. If I start out with this model here, I have trouble with the last step, and I still do, and I'd never use this model, so I don't see the point in this. I may throw it in a little bit later, but not now. Putting a current source in series with another current source does not change the current source. Why would you do that? Of course, this is why this is what I'm thinking at this point too. Since the current here is 0, I could connect that node across. And then I do then there's magic happens and I do a source transformation and I turn this into an equivalent resistance of 1 over GM. One of those current sources gets transformed and I get something that looks like this. I don't completely understand this step and I don't use this enough to care. But these are two, and if you really care, it's in the book, and they are equivalent models of the transistor. This is my workhorse right there, A. If I can get away, and I can get away with that 99% of the time. It's not worth figuring out. So we've looked at the common source. We're eventually going to work our way into 4 types of transistor amplifiers. They're the only 4 I can get out of a single transistor: common source, common gate, common drain, and common source's evil little brother, the common source with source resistance. It makes the circuit analysis a little harder once we get to this. Now, every time we build an amplifier, the guys who are not amplifier engineers, and I don't understand why they're not, they don't care about the inner workings of my amplifier. Or if I'm working at a system level block diagram, I don't want to have to think about what this amplifier is doing every time I look at the amplifier in a system that includes 12 other ICs and a whole bunch of stuff going on. I want a simple linear model for this. And the simplest linear model, and this is like, is to look at this amplifier and treat the whole amplifier, this triangle part right here, as being what's inside this blue box. I don't care about the details. I don't care if it's common source, if it's a diff amp, if it's a cascode, whatever it is. The only thing I care about is what's the input resistance, what's the output resistance, and what's the gain. And if I know those 3 numbers about my amplifier, I have pretty much nailed down most of what's going on first order. I can figure out all the fine details later, and I can simulate them. Now, the thing I want to know is about what is the perfect amplifier. If I look at, change colors. If I look at this front end of the circuit here, this is like a standalone circuit. I've got a voltage source and I've got 2 resistors. The voltage that makes it to the input is just going to be a voltage divider. So Vn will equal whatever V sig is. And I am crashed. I'll be back. We are on slide 21, number 30.